worried about developing the equations that the Smith chart is based on, even though I kind of ran through them and I put the solutions there. What I want to do is show you how it's applied. And what I'm going to do, and I hope everybody has this, you need basically a compass and a straight edge to do this. And I'm going to start by doing a simple problem. And here, we're going to do something called impedance matching. I'll put it here. So this is going to be impedance matching. Now, I didn't give you a bunch of problems about the Smith chart, but does everybody understand how to use a Smith chart to find to first enter the Smith chart? We'll go through this one. Let's say I just want to make sure everybody's got this. If this is a characteristic impedance Z naught, and we have a load ZL, and we're at a distance L down the line, and I want to find the input impedance here. So this is what I'm after, my input impedance right there. Follow me on this, class? Let me give it some real values so it'll have meaning. Let me use Z naught equal to 50 ohms, and let me use ZL here equal to, say, 25 plus J 50, all right? And this is an arbitrary value. So if you're using a Smith chart to find the input impedance, or basically the impedance of the line at any point, at any distance L away, your first step is what? Can anybody tell me? Anybody at all? This is from Friday. What do? We normalize the impedance, right? We say whatever the load impedance is, we divide that by Z naught. Correct, class? Now, when we do that, we end up with what? We get 1/2, right, plus J1. Do you all agree with that? Everybody? Can you all hear me okay? All right.
Yes.
So now I got to find that on this Smith chart. I've got a bigger one today. I blew it up a little. So here's my Smith chart. And if you have a Smith chart, please, do y'all have Smith charts in front of you or not?
I do.
All right. I recommend printing out 10 or 20 of them. And if you want to blow the thing up, make sure it's proportionally blown up, go ahead and do it. So if I have this, when I look at 0.2, or I mean 0.5 plus J1/2, the 0.5 is right here. This is the 0.5 line. If you can see it, it's the real part, and this line would be 0.5, and I'll try to blow that up for you. So y'all, well, I mean, y'all can see that, can't you, on your Smith chart? That's the entire circle right here is a value of a real part of 0.5. Now, the imaginary part was 1. And you can see this is the imaginary part. This would be J1. So where these two intersect is right here. If you come and trace that line, and that point is 1/2 plus J1. And that's where ZL is. And normally I tell people to label that as 1. Whenever you're doing Smith chart problems and you're going to hand them in, you always place a number or a letter at each point and go in sequential order. There's where I came in. Now, the next thing you do is take a straight edge of any type. I'm using blue pen for this, and draw a line through that point. This is actually, this pen, you normally use a finer tip pen, or finer tip pencil. And then out here, where it says wavelengths towards generator, it's the outer rim, because we're at the load, so the only choice we have is moving towards the generator. Does everybody agree with that? You can't move anywhere else but towards the generator if you're at the load. So this number right here, if you look at that, what do you get? About 0.13, about 0.13, let's see, 24. So that's about 0.13 4 lambda. Can you confirm that? Take a look on your Smith chart. If you have a sharp pencil, you might get a little better resolution. You all see that, class? All right, take a look. That's about 0.134 lambda. All right, now what we're going to do is I'm going to decide how far down the line I want to go. And I'm going to tell you one thing. Every time this length L becomes a half wavelength, I move all the way around and I go through that point. What I'm trying to do is tell you, this is what I should do really. I should take my compass right here. If you have one, go ahead and do what I'm doing. Have the compass align with that point and circumscribe a circle there. Now this might be hard to see, but I'm trying to show you that I'm just putting a circle centered at the origin of the Smith chart, right there, of radius. It's equal to this right here. And by the way, this is the magnitude of the reflection coefficient right here. Can you all see that? Now that's the magnitude. If you come down here to the base here, you're going to see something that says standing wave ratio here on yours. And if you put yours right there, you got to start from the middle and move over, you'll see that this is in fact the standing wave ratio, which looks like about 0.45. And we can calculate the standing wave ratio if we want to, but this will give us a close estimate. Are you with me, everybody? I frankly don't really use this. I just use a calculator or a computer to calculate that. But this is back in the day when everybody had to use slide rules, so this is quicker. Do you all know what a slide rule is, by the way, or not? I'm curious. How many know what a slide rule is? Just show him.
I know what it is, but I don't know how to use it.
A slide rule was this, and this is what I actually started to learn when I was in high school instead of a calculator. It is basically a ruler with an insert in between that can slide back and forth and a piece of plastic on the outside that'll let you do calculations like log of numbers, 10 to the power X. You can calculate these values very easily with a slide rule, and you can do complex calculations. So before calculators were available, like in the 40s and 50s, and even before that, people use slide rules to do all your calculations that you're punching into your calculators, including characteristic impedance and stuff like this. And they didn't have calculators, so they had to rely on things like Smith charts and all these little tables that would allow you to calculate things quickly just from that, without going through the calculations with the Smith chart. Follow me, class? All right, now back to this problem. I'm going to go ahead and say this. Make sure you understand this. I can go any length away, and I'm going to extend this line and tell you a few things about the Smith chart to make it a little more clear. Because there's a lot we can talk about, and I'm trying to do this in an order that will make sense to you. That's the entry point. Now some of the interesting characteristics. This is ZL right there, right? This point right here. If I go 180 degrees around here, I've moved exactly a quarter wavelength. Because the entire, if I go around at 360 degrees, or just go back to my starting point, then I move half wavelength. Now the way I move is at this radial distance. When I say move, it's like I'm going to be moving along the outer rim here to a different point. And I'm going to say this, suppose I move a quarter wavelength. So I'm going to say this. If L here becomes a quarter wavelength, or 0.25 lambda, in order for me to find this point, I can draw a straight line right through there, and I know that's a quarter wavelength away. Or I can go ahead and I can say, well, the mile marker here was 0.134. I'll add a quarter wavelength to that. So I have 0.134, and I'm going to add 0.250 to that. So that's 3, right? It's 0.384. Do you all agree with that, class? We're just adding, see, these are increasing numbers. We're here. If we add a quarter wavelength to that, we're going to be down here. Now, if you look at your paper, on the bottom here, I don't know if you can see it. Let me try to blow that up for you. It's starting to get bleary though. That's 0.38. That's 0.382. That's 0.384. So it's just about hits it on the head. So that's 0.384 lambda. You followed me on that, class? I want to make sure you see that. Now this impedance right here, just put a dot there. That's my 0.2. And what this impedance would be is, and I want you to take a look at this, the real part is going to be what? If I trace that up, I get about 0.4 for the real part. Do you get that? Check it out, people. See if you can find that. So for here, when I look at now my Zn, that's normalized Zn, it's 0.4. And what's the imaginary part, class? Come down here and you get, that looks like 0.8, isn't it, class? You see that? Can you all see if you take this point and you trace out the line that intersects it right here, this is going to be a line that always comes in perpendicular to the outer circle, and these are the imaginary components. Here, do you all see 0.8? Let me just see. How many do? Just some way indicate that. I got you guys. Anybody not see it? All right. It should be very clear and evident, right? Isn't it, class? Now, that's a negative though. So make sure you put down here, negative J 0.8. And all these values where these lines intersect perpendicularly here have a negative J sense to them. And it's important you understand that. So all the values down here, right, where the lines are perpendicular to that, have a negative J sense to them. All the values up here have a positive J. Are we with me? Everybody with me on this? Let me reduce the magnification. So now, when I look at this, I see my real part is 0.4 imaginary minus 0.J8, so minus J 0.8. And I want to show you something here. Remember I told you that this point, if I go a quarter wavelength, this point will be exactly 1 over ZL will be the impedance. Do you all remember that? Every time you go a quarter wavelength from a point on the Smith chart, the impedance becomes 1 over the impedance. And I can prove that to you. I'm going to do it right here. All right, where's my math cat? Let me go down. So I had a normalized ZL here, and I had it equal to 0.5 plus 1J. Didn't I, class? All right. Now, the magnitude of that, or better yet, let's just do this. 1 over that, 1 over ZL would be equal to 0.4 minus J 0.8. That's exactly what we got, isn't it, class? So that's the normalized impedance. Now, something I have to say, if this is the normalized impedance right here, and I hope, can you all see it right there? Remember the way we got that, we divided by Z naught. So if you wanted to know the actual Z naught a quarter wavelength away, you would say that Z, the actual Z a quarter wavelength away, would be equal to 1 over ZL, or looking at the Smith chart value, and it would be times 50, because that was the actual value of the characteristic impedance. So it would be 40 minus, or 20 minus J40. Do you follow me on that? So the Smith chart, if you wanted the value of the impedance any point away, you just take the normalized impedance and multiply it by Z naught. Does everybody understand that, class? You good with that? All right. Now, some more information about Smith charts that'll help, I hope. The Smith chart's getting messy. That's okay. Next thing we talk about is what happens if I go not a quarter wavelength, but suppose I go 0.4 wavelengths. Now, I want you to see this. When I start moving, as soon as I go through this point, you see how this is 0 here? You know, it's coming around. Look at this distance. The distance on the outer rim, 0.47, 0.48, 0.49, and then it goes to 0. So what that tells me is if I add a distance to this that causes this value to be greater than 0.5 lambda, I'm going to subtract 0.5 lambda from it to find the actual value of the impedance. Let me give you an example. Are you with me with this one so far, class? With me? Now I'm going to do this. I'm going to say I want the impedance to this same setup here. Z naught is equal to 50. ZL here is equal to 25 plus J50. And normalized ZL is equal to 1/2 plus J1. That's all the same. But now I'm going to say let the length of this line be equal to 0. Let's say 4 lambda. Now, follow me on this. My original point was right here. That's where I came in at, right? You all follow me? I'm going to add that additional distance. So I'm going to say 0.134 lambda plus 0.4 lambda will give me 0.534 lambda, right? Y'all see that? Now here's the thing. Anytime you have more than a half wavelength, if this was like 0.634 or 1.654, you're going to keep subtracting off half wavelengths until it becomes less than a half wavelength. So if I take this and subtract off 0.5 lambda, that becomes 0.034 lambda, doesn't it? Go ahead and do it. Make sure you see what I'm doing too. 0.034 lambda. I'm sorry. I'm looking at you, and this thing is, that's what I've done. When I've added 0.4, I get this value, but this is greater than 0.5 lambda, so I have to subtract 0.5 lambda. What I'm really doing is this. See, every time I go around, and think about this, every time I go through there, I go through 0.5 lambda, which is the same as 0. So I have to subtract that number to find out how much further I went up. Does that make sense? All right, and when I do this, I ended up with 0.034 lambda. So if I look here, this is 0.04. I hope you can see this. That's 0.4. So 0.034. This 0.03 would be about here. Can you all see that in yours? I'm looking for 0.034 on this outer wavelengths towards generator. Do you all see that, class? Can you all see it in your Smith charts? All right, now you take your drawing tools and you just take a line. This is real faint. I'm sorry about this, but that circle I made, but then you have to run it through there. You don't have to run it all the way, but you can. And now where it intersects this circle, I don't know if you can make out, it's so faint. You see, this is that pencil that the circle of constant reflection coefficient. So this is the point I'm talking about right there. And I want to find now what the normalized input impedance is right there. This is at 0.4 lambda away. Are you all able to see this, class? Can you make out what I've got here on the screen? Do you have a question, anybody? Now's a good time to ask. What we're after is the input impedance at 0.4 lambda from the actual load, okay? With me? I'm just trying to look at faces and figure out. Okay, I'm guessing you're with me. So what do you read for that? Can somebody read it off on yours? What's the real part? What's this part? Remember, you got to follow that circle down. What do you get? Anyone? Can anybody do it? I'm looking for this. Don't look at mine. Look at yours. This is going to be lower resolution. Isn't that 0.2 here on yours? And that's 0.22, 0.24. Isn't that about 0.24? Can you all see that in your Smith chart? Are you getting about 0.24 for the real part there? Okay. So the real part is 0.24. What's the imaginary part? Here's where you got to take a look at this line shooting out right here. Well, actually, it's this line. What do you get? Take a look out there where this intersects right here. Can you all read these numbers? That's 0.3, right? That's 0.2, so it's 0.22, is that right? Plus J 0.22. Take a look on yours. Can you see it? This number is about J 0.22, isn't it? Go ahead, check on yours, guys.
Could you explain one more time how you got that point?
Yeah. What I'm looking at, this is let me get a different Smith chart. Because this one's kind of icky. Now, I'm going to just say this so everybody knows it. If I put a dot here, all right, there's an imaginary, or there's a line that moves through this way. These are like the latitude and longitude lines on a globe, only consider it a projection on flat paper instead of a round surface. So you're going to get a conformal mapping. The one that hits this perpendicular, if this is the point right here, this will be the imaginary component. So that's J1, if just on the point I put. See it? Because you can read 1 there, can't you? If you look over here, that's J1.2. This is 1, that's 0.9, that's 0.8, that's sorry, you can't see this. This is J.1.2. If this point's where I hit, then this is the imaginary part. It's just a trajectory of this line that's really a circle centered somewhere up here. And the real part would be down here. Now, the real part you see is 0.4, but it's where the two lines intersect. They're conformal. They're always at 90 degrees to each other, where they intersect the point, but they have a trajectory that's going to be a circular. So it's not going to be straight lines. It's like projecting the latitude, longitude on a globe onto 2D. You get this conformal business, all right? Now, the point I had was way out here, right? This is the point right here, right? Can you all see what I'm talking about? That's the point we're talking about, right? Now, where's the real point? Can you see how this it gets a little tougher to read, but comes down here and it intersects here at a point about 0.24. Isn't that right, class? How many can see that? I need to know. Carlin, can you? Okay, you can see that, right? Now, take a look at the line that goes perpendicular to it on your Smith chart, not mine, and see where it intersects this line right here. About here, right? And on your Smith chart, if you read this, you should see 0.2 about here, and this will be about 0.22, 0.24, somewhere in there. How many can see that? Can you see it, Carlin? You asked about this one. You can or not? You can? And I'll give you a tip. I went and I got my drawing tools, This is a good compass. They're cheap compasses. I wouldn't use them. You'll get incorrect answers. Find yourself a good compass. You can order it online, and make sure you have sharp points. And I don't think you have to take drafting or graphic arts. I had to in college. This is something that'll put a razor point on your stuff, so you can get very clear and high fidelity drawings. This is back in the day when people actually, even electrical engineers, took drafting. And it's called graphic arts. Okay, now, what do you guys read for this point on yours? I'm just curious about, for the imaginary part. Anyone? What about you, Tyler?
Mine's pretty close to that.
Hey, Ben, are you recording this?
Yeah, I am recording this.
All right, can you see this all right?
I can see it all right.
Do you have a Smith chart in front of you?
Yes.
All right, can you see it on your Smith chart?
For that Z endpoint?
Yeah, I mean, I want to see to make sure you can see this as J point 0.22.
Yeah. Yeah.
It's harder to see, and here's why. There's a lot going on here, and these numbers are small on the outer rim. Familiar with that, everybody? All right. So remember, the thing is, anytime you're dealing with things that are larger or smaller than a half wavelength, you subtract off a half wavelength. Something else, if you get a value that's negative, then you add a half wavelength until it becomes positive. Okay. And I'll give you some examples of this as we go. Now, while I'm on this, just to rehash a few things, if I'm here, this is where I came in at, right? That was where the load is, right, everybody? That point here corresponds to being right here at the load, normalized, right? Now, how far from that load do I have to go before I hit a voltage maximum? Do you remember what I told you on Friday? Anyone? Where's the voltage maximum? I'm moving right away from the load. How far do I have to move before I hit a voltage maximum? Anybody? There's one thing I told you. I said wherever that circle, the constant radius circle, intersects this axis, that's Vmax. So this is Vmax here. This is Vmax, would be this distance right here. And how far would that be? On your Smith chart, what is this number right there? Anyone? Outer rim, wavelengths towards generator. What do you read right there?
.25.
That's right. Don't forget that number. It's 0.25. So the distance from here to here would be 0.25 minus 0.134, which means, if I come down here, it means that the voltage maximum Vmax would be at a distance L equals 0.25 minus 0.134 lambda. With me? And that's going to be what? 0.124 lambda, isn't it, class?
Can you slide the paper over, Professor?
Oh, I'm sorry. Yeah, thank you very much. So really what I'm saying is if I have 0.25, that's how far I have to go. I have to go to that mile marker, and I had to subtract the mile marker I'm from, 0.134, and that's the distance, or 0.124 lambda away, and that would be a voltage maximum. Got it, everyone? So that's a voltage maximum. And by the way, if you look at this, I want to make one point here. When you look at this, what is the normalized impedance there? Right at this point where I cross this equator, What's the normalized impedance on yours? Just take a look. Anyone? Can anybody give me a best shot?
About 4.4.
And that point is the standing wave ratio. Right where it crosses the equator, you know, these are circles of constant reflection coefficient and magnitude, but the actual angle changes. When it crosses this point, you get the standing wave ratio. And it happens to be also something that's strict real. There's no imaginary part. So the input impedance would be Z naught times the standing wave ratio at this point. All right. Follow me on this? And this will be the maximum value. This far away will be the maximum, or where the maximum impedance occurs, and where the voltage will be a maximum. Can everybody hear me okay? Now, if you go a quarter wavelength away, keep going from there, keep going around that circle. All right, I'm going to keep going.
Could you
And
slide
go-
the paper over a little bit?
So I'll try to look there first. So this is a voltage maximum. It's also impedance maximum. So this is max Z as well. Max voltage, and that's the standing wave ratio. But if you keep going around, you go a quarter wavelength from there, then you're going to get an impedance minimum. That would be Z min. And it's really just 1 over the standing wave ratio would be the value here. And you're also going to get a current maximum. So the maximum value of the current is a quarter wavelength from the maximum value of a voltage. These are things you need to be at least aware of. All right, and that's the minimum impedance. Now, how many have compasses available to you in straight edges now? Just raise your hands or show me. In front of you now. Fowler, do you have that or not?
I do, but my compass is really bad.
Oh, Caleb, okay, your compass is bad. All right. What is it? Yizong Wang, do you have that? Or Kenny, do you have a compass, a straight edge? You guys need to get a compass and a straight edge, a good one. By next lecture, you're going to need it for the homework. This stuff is not easily doable with calculators, by the way. You can write programs for it, but it takes some time. This is really something that you're going to use over and over again, even in the power industry. I talked to Dr. Charlie Gross, and he even has to use this stuff occasionally in power. So you don't get away from it when you're done with this course. It permeates a lot of engineering. Now, we went through how you get into the Smith chart and normalize. We went through how you find the impedance going along that circle of constant radius, or really it's the magnitude of reflection coefficient. How you can get the impedance anywhere, correct? Now what we're going to do is find out how you would go about using a Smith chart. Something else, we found the maximum value of the voltage, and the standing wave ratio is right here where it crosses the axis between the center and the rightmost part of the Smith chart, or the equator on the right. And we found the minimum value impedance over here, right? Now what we're going to do, and the minimum voltage as well, what we're going to do is find out how to use a Smith chart to do matching. And this is key. And when I say about impedance matching, I'm going to tell you, it can be by adding elements like resistors or capacitors. I'm sorry, by adding elements like inductors or capacitors in series or parallel, or it could be by adding pieces of a transmission line itself in series or parallel. This is impedance matching, and it's very important. I have to send one piece of information to a group. Give me 1 second. If I can. I'm supposed to be at a meeting at 9, but I can't. So just hang on for a second. Sorry, I just sent that. So I'm going to get in trouble. Back to this. Back to impedance matching. I have several things worked out here and examples that I want to do, but I recommend you start this one with a new Smith chart. So we might as well go ahead and do impedance matching using a real element in series. And here's what I'm going to do. Why don't we do the same basic problem? So I had basically this. I had some characteristic impedance, and I had a load right here. And what I want to do impedance matching is this. Now, follow me on this. You know that if I have a transmission line, right, with characteristic impedance Z naught, if my load impedance is Z naught, right, then what's the reflection coefficient at the load, which is V0 minus over V0 plus? In other words, if the load impedance is equal to the characteristic impedance, what's the reflection coefficient? Well, what's the definition of the reflection coefficient? It's what? Don't all talk at once. Anybody? Participation helps, believe me. I'm not just saying this. It's what? ZL minus Z naught over ZL plus Z naught, right? And what is that value? That's the point I'm getting at. 0, right? If ZL is Z naught, it's 0. Do you agree with me? It means nothing's reflected. That's our goal. Can everybody hear me okay? That is the goal. So how do we do it? Now listen, this is how we do it. You know how when we get ZL, that's equal to, when we get small z, that's really going to be the entry point, ZL, and that's ZL over Z naught, right? Agreed?
Yes.
That's how you enter the circle. Now, if I can move, and I know this is going to have a real and imaginary part, it'll have some R plus JX. Now, if I can move until R is 1, so I'm going to move until I have the Z, the input impedance being 1 plus JX. Now, listen to me. What if I added a component at that point to get rid of this JX? So what I'm going to say is you're going to move a distance L until the normalized input impedance Z would be equal to 1 plus JX. That's your first step, and I'll take you through it. Follow me? I'm going to move. Once I come into the Smith chart, I keep moving until I hit 1 plus JX. And X could be a negative or a positive number, but I have a real value of 1, right? Now, I'm going to, at that point, when I have the real, I'm going to add an element, this time in series, because it's an impedance, that will be minus JX. So when I add minus JX, now the impedance at this point, the normalized impedance, will be just Z here would be just 1. Do you follow me on the other side? I want you to think about what I'm doing. I've got an input. First, I take a load impedance, and forget about Z naught here. I have a load impedance. I normalize it, and now I'm moving. I'm going to move until I hit the point where the normalized impedance will be 1 plus JX. And then I'm going to add an impedance that would be minus JX. So the net impedance on the other side of it would be just 1. That's normalized. And then when I unnormalize it, I have the characteristic impedance going in here just be equal to Z naught, and the reflection coefficient would be 0. All right, now that's my goal. So now I'm going to do it for a problem and show you how this works. And we're going to calculate the values. For these things, if we use elements, you have to have a frequency. So I'm going to give the frequency as, say, 1 gigahertz, 10 to the 9th hertz. Okay. Now, and let's give the problem. I'm going to have a characteristic impedance of 50 ohms. I'm going to have a load impedance equal to, say, 25 plus J50. So that means the ZL normalized is equal to 1/2 plus J1, just as before. Correct, class? Now I take my Smith chart and I locate that point. And that point, 0.5, is right here, right? And J1 is right here. So this would be my 0.1. That would be ZL, which happens to be a 1/2 plus J1. Y'all see where that is? How many see that right now? Let me get a look at your faces. Go ahead. If you're doing it, go ahead and do it. It's best you make sure you find that point. You got it, Caleb and
Yes, sir.
Carlin? Can you see it? All right. That, and always put the 1 there. That's where you're gonna. Next thing, well, you can take your straight edge right now, this, and just go from the center of the circle through that point, draw a line out to the outer point, and you're going to get a mile marker of 0.134 lambda. This is from before. That's your mile marker where you start. Now, our goal, now you have to take your compass and you have to go ahead and make a circle. Get a good compass when you do this. Like that. It's faint on mine. I don't have a dark ink. And listen to me. I said we're going to move from the load until we hit a point where the real part will be 1, and you're going to have some imaginary part. So I want you to keep watching here. Where's the real part 1? You see how this is the 1 circle here, class? This is the very important part. This is the R equals 1 circle. Y'all see that? Isn't that R equal 1 right there, right? If you just go right at the center point of the circle and then find the trajectory of the circle that's symmetric about the equator, that's the R equal 1 circle. That's the one we're always going to go to. We want to intersect it. Now you'll notice if I'm moving from the load, right, I'm going to hit that point right here. Do you all agree with that? I intersect it there, so I know that's going to have a real and imaginary part. And this point right here, and here's how you do it. You take your straight edge again. We're going to figure out how far we have to move. And we're going to take that and shoot a line right through it. You can do it with me. And here, I'm going to say this is 0.172, 0.174, about 0.175 lambda. You get about that? Go ahead, try it. See what you get. Now this point right here has an important value. This point has a value of 1 plus j. Try to estimate that. When you come up here, you get 1 point j what? 0.4, I mean 1.4, 1 point, sorry. That's 1.6, so it's about j 1.5 right here. So this is 1 plus j 1.5. How many people see where that point is? Give me a show of hands. I got 1, 2, 3, 4, 5, 6. Okay. Now, how far did you move? Well, I started at 0.134. I ended up on 0.175. So the distance I moved, and I'm going to get to the other sheet of paper, the distance I'm going to move until I put the stub on, I'll call it the length of the main line, would be equal to 0.175 minus 0.134 lambda. And Dr. Wentworth's book will call this L, and then he'll have either, he calls it through, I think. I just indicated L. I don't mess around with that. So for the actual problem we have when we're doing impedance matching, we're going to move a distance. And what is that? That's 0.041, right? So 0.041 lambda will be equal to this distance that we move from the load. And this will be ZL here. Now, at this point right here, my input impedance right here is Z equals 1 plus J 1.2, correct? Or I'm sorry, 1.5, my bad. It's J 1.5. Do you all agree with that, class? Right? Everybody see that okay? Trying to read it. Are you with me? Now, if we have that, we want to get rid of J 1.5. So first, this is the way I do it. Calculate the actual impedance at this point. So the actual input impedance, Z in right there, would be equal to 50, right? Because it was a 50 ohm line, plus J, well, 1.5 times 50 is 75, isn't it? You all follow me? I'm calculating the actual impedance at a distance of 0.041. The real part is 50, the imaginary part is 75, correct, class? I want to get rid of this J75. If I put a series element, what would get rid of it? What series element has a negative J impedance? Think about it. A capacitor. Think about it. In a capacitor's impedance, 1 over J omega C. 1 over J is minus J omega C. So what I'm going to do is put a capacitor in series with it. And I want this capacitor to have an impedance of minus J 75 ohms. How many understand that? Got me? I want to get rid of the imaginary part. Now, the impedance of a capacitor is minus J over omega C, right? That's the impedance of a capacitor, correct, class? You can call it X sub C, if you will. And that has to be equal to minus J 75, doesn't it? To get rid of it. Because we had plus J 75, we want to get rid of it. And that means the capacitive value would be what? I would have 1 over omega C equal to 75, or I would have C be equal to 1 over omega times 75, correct? Or really 1 over 2 pi F, or times 10 to the 9th, times 75. And that means your capacitor that you would put in series with that at a frequency of 9 megahertz, or I mean at 1 gigahertz would be equal to C would be equal to 1 over 2 pi times 10 to the 9th. Times 75. Oh, come on. So it's 2.122 picofarads. I'll go back to sharing my screen. I mean, go back to the Zoom camera. I mean, the document camera. Now, how many see that right there? You all with me? Keep watching. Now what happens, that's one point that I could do impedance matching at, but keep going down here. We're going to keep going. And right here, you see how you intersect the one circle again, don't you? This is, call this point 2, and this is 2 prime. Now, this would mean you have to put this the element you're going to attach a little further away from the load, isn't it right, class? This is short distance. Now moving to here, it's a little further, right? What's the impedance at this point, the normalized impedance? Well, it would be 1, right? Can you all see that point okay? That's where it intersects the 1 circle. This is my circle that I put on there with my compass, and here's the 1 circle, isn't it, class? Can you all see this? This is the 1 circle right there. Can you all see that? Now, that point right there will have a real value of 1, but what's the imaginary value? It'll be minus J 1.5. If it was plus J 1.5 here, when it hits this point, it'll be minus J 1.5. Are you with me? Now, if I wanted to get rid of that impedance, I wouldn't move this distance, I would move this distance. So that means you have to take your straight edge and you have to draw a line from the center right through that point. And then you have to look out here on the rim, wavelengths towards generator, and you have to figure out what that is. And I'm getting a value of 0.322 about. This is about 0.322 lambda. Check on yours, see how many people see that in yours. You got 2, 3, 4. Anybody else? 4, 5, okay. Hopefully you all see that point there, right? Now, how far did we have to move from the load to this point, class? Well, we started at what, 0.134 lambda. We ended up on 0.332 lambda, right? So the distance we'd move for the second case would be, this is ZL. Oh, sorry. This is the ZL here. Now we're going to move a distance here. I'll call it L would be equal to 0.322 minus 0.134 lambda. And
Could you scoot it up a little bit, please?
yeah. That's how far we're going to move, right? We've taken the point we ended up at, subtracted from the point we left. These are the mile markers or wavelengths towards generator marks. All right, and that's how far we go, right? How many see that right there? Guys, okay. Now, if you see it, you can do the math on this one in a second, but that means the input impedance right here is going to be, at this point, that's going to be equal to 1 minus J 1.5, right? All right, you agree with me there? Right, in other words, this point right here has a normalized impedance of 1 minus J 1.5. We need that 1, that's what we're after. That means the actual impedance right here, the actual impedance, Zn, would be equal to 50 minus J 75. Do y'all agree with that? Right? That's when we multiply it by the characteristic impedance that we initially used to normalize it. Now, once we have that, we have to get rid of this minus J 75. So we want to add plus J 75. Do you agree? How many see that? Plus J 75. And that what element has an impedance that's a sense plus J, class?
An inductor.
Right. Now we want an inductor here to have impedance of J 75. And this is characteristic impedance of 50. And this load was equal to 50, or I'm sorry, was 25 plus J 50. All right, now so I've got to calculate the value of that inductance now. I hope you can see this, okay? I'm putting an inductor in here with an impedance of J75. So that means J75 is equal to the impedance of an inductor. And the impedance of the inductor would be J times omega L, right? Isn't that the impedance of an inductor? And that means what? That L would be equal to 75 over omega or over 2 pi times 10 to the 9th, because I made F 10 to the 9th. Do you agree with that, class? All right, now that's adding a series element to do impedance matching. But we could also add a shunt element or an element in parallel. All right, that would be adding an admittance. Does everybody follow me on that? All right, give me a second here to finish this thought. If I'm not in the President's Council meeting, it won't be a problem. He'll get over it. Next. We're going to do this same very problem, only we're going to use admittances. All right, admittances are 1 over impedances, right? So if you're with me, I'm going over again. Get yourself a Smith chart, bring it there, and now we're going to do it with admittances. So the first thing you have to do is locate the normalized impedance, and that was 0.5 plus J1, right? Class?
Yes.
And I'm going to use the same load. So 0.5 plus J1, well, there's J1, 0.5 is right there. So there's my first point, and that's ZL. This is going to be a little different. So here, I know some of you have a class coming up. I just want to show you the final point I want to make today before I get into stub tuning tomorrow or on Wednesday. Now, go ahead and circumscribe that circle. You know, they have a big Smith chart in downstairs brown. I wish I could access it on the wall. All right, that's point 1, right? I already know what I'm going to do. I'm going to take my straight edge and I'm going to draw a line right through there out to the mile marker, and I know what it is already. It's 0.134 lambda, right? Now, here's where things take a turn. Take this line and extend it right through the other side here. And you're going to get a mile marker down here that's a quarter wavelength from this one. So if you had 0.25, you're going to get 0.384 lambda. So here it's 0.384 lambda. And I've got a point to make here. You see how this is impedance right here? This is normalized impedance. Well, the opposite point right here is called YL, and that's 1 over ZL, and that is admittance. That's normalized admittance at this point. That was point 1, this is point 2. Can you all follow me in that, class? Are you with me?
Lester, what's the symbol you're using there? Is it a cursive Y? Or
It's just a simple script Y sub L. In Dr. Wentworth's book, you'll have a small y sub L. It means normalized admittance. It's just 1 over the normalized impedance. Now, what I'm going to do now, I'm going to put something in shunt, or I'm going to look at it as an admittance, not an impedance. This is a little different for you people because most of the time you're used to dealing with resistances or impedances, right? You're not used to dealing with admittances. But the reason we're using an admittance is because admittances add in parallel, just like in the way impedances add in series. You just add the numbers up. So I'm going to move from here. That's still going to be wavelengths towards generator. I'm going to move around this circle. Keep going, keep going. You'll notice I'm moving right through the load point right here that I came in at. So I'm moving a quarter wavelength right off the bat. And now I'm going to move to the point where I intersect the 1 circle. And here's the 1 circle. I'm going to move to the point where I have 1 plus J And it should be 1 plus j 1.5 is the value right here. Do you all get that? That's 2. This would be 0.3. Can you all get that, class, about that? Now, you would take your straight edge and you draw a line through here. And we're repeating a lot of the same steps we did before. We take a look at the mile marker out here. And what do you get? 0.175 lambda, don't you? Same as before, roughly. Correct, class? How many see that? I got to show you this. Well, how far did I move from this point to this point? You always take the position of the point you ended up at. So here's how far I moved. I ended up at 0. This is how far I moved in the length of the line. I ended up at 0.175 lambda, and I have to subtract from it the point I came from, which is 0.384 lambda. 384 lambda. What do you notice about that value?
Negative.
So when you get that value, we're going to add a half wavelength to it. And I'll tell you exactly what that value is because some of you want to know. So it's 0.175 minus 0.384. And that's minus 0.209. So what I do is then add half wavelength to that. Anytime you have a negative value, just add a half wavelength, 0.5. And my new point, I'm going to end up, my length of the line or the new point would be, the length I would move would be 0.291 lambda. I guess what I'm trying to say is moving from here to here is moving 0.291 lambda. If it was exactly a quarter wavelength, I'd be back here, but it's a little more, it's 0.291 lambda. So that means when I'm going to do this one, I'm going to move, here's my load impedance. Now I'm going to move L equals 0.291 lambda. And at this point, I have a normalized admittance, not impedance, but my Yin would be equal to 1 plus J, when I hit that circle, 1 plus J 1.5. Work with me on this one. Do y'all agree with that, class? I know remember, this is in the admittance domain, so it's normalized admittance. I'm moving until you always go to the 1 circle. So when I hit the 1 circle, my first point is 1 plus J 1.5. How many agree with that? It's just like before, right? Now, this is an admittance. Think about admittances. If I talk about capacitive reactance, that's what? 1 over J omega C. If I talk about admittance, it's 1 over X sub C or J omega C. Follow me? How many understand that? When I talk about impedances, X sub L, it's equal to J omega L. When I talk about admittances, it's 1 over X sub L or it's 1 over J omega L. This is important. This is the domain we're in now, admittance domain. Now listen to me carefully. This is a normalized admittance. So in order to get the normalized impedance, we have to, to get the unnormalized admittance, we have to divide by Z0 rather than multiply. So we can now say that the actual value of Yin would be 1 over Z0 plus J 1.5 over Z0. Are you with me? This would be the normalized admittance. You take 1 over that, you would get the input impedance. Are you with me, class? You've heard of admittance before, right? In circuits, you're familiar with that term. And 1 over resistance is conductance, 1 over impedance is admittance. That's the way you think about these things. Now, right here, when I have this over Z naught, what I want to do is add an element to get rid of this. But with admittances, you add them in parallel, not series. Follow me? So I would like to add an admittance of what? Minus J 1.5 over Z naught. Do you all agree with that? So what am I going to add that would have it? If I'm going to put something in parallel with this, what would it be? I'll just give you the bottom line. It would be an inductor. All right. The inductor would have an admittance of minus J over omega L. Or sorry, minus J over omega L. And what that means is, to get the value of L here, I would say 1.5 over Z naught would be equal to 1 over omega L. Follow me on this one, class? And therefore, L would be what? L would be, think about this, we could invert these things first of all. So we'd have Z naught over 1.5, right? And then you'd have to divide by omega. And that would be the value of L. Follow me? Now this is admittances. It's just like impedance matching in series, but we're putting things in parallel. So we're in the admittance domain.
Can you move it down a little bit, please? Or up?
Yeah, this is what I'm saying, that this would be the admittance, right? The admittance of an inductor is 1 over omega L, 1 over J omega L, actually. Well, it has to be equal to 1.5 over Z naught, because that's the value I'm trying to get rid of. I'm trying to get rid of this. So I'm left with just an input admittance of 1 over Z naught, which would mean the input impedance would be Z naught. And that means I would have the reflection coefficient of 0. Everybody follow me, class? Give me a thumbs up. Now, I'm going to tell you one other thing, because I'm running out of time here. I should be in the President's Council meeting. That's one point. Y'all know you can go to this point as well, right? And here you're going to have 1 minus J something, correct, class? With me? Show of hands. I know I'm running over, forgive me. So now you would add something in parallel that would have an admittance of J, positive J, and that would be a capacitor. Capacitors, there's admittances J omega C. I'm going to give you some homework. This is just impedance matching with elements. And they do this, they have to solder in small little inductors and capacitors to do impedance matching. It can be tedious, but it's effective. On Wednesday, I'm going to go through impedance matching using transmission lines, where we either put a short or an open circuit at the end of the transmission line, and we replace the elements that were either in series or parallel with actual pieces of transmission line, finite lengths. And this is done all the time. It's called stub tuning. And you can read about the section in the book. I'll give you homework. Please do it before class and keep up with this stuff, because if you get behind now, it will be very difficult, in my opinion, to catch up. There's a lot of stuff here we're going to use over and over again, okay? All right. Any questions before I go? I know I ran you over, but this is an office hour. Anything?